Okay, so we're gonna go through contraction of smooth muscle. Here's my little drawing, just kind of showing how it's different than skeletal muscle, where it's not aligned in series like what we usually see, that they're kind of put in different geometrical shapes to allow for a different type of contraction, and how we would have myosin filament and then we have actin kind of just surrounding that myosin filament. Okay, so this is a contraction of a smooth muscle cell, visceral smooth muscle cell, aka single unit. What was I gonna say? Or single unit, multi-unit. The inside of it like works the same. I only put specifically that it was a visceral smooth muscle or the single unit muscle because I was kind of showing the axon with its varicosities, and I was just trying to insinuate like this would be like stimulating a GI tract or something like that. But single unit, multi-unit smooth muscles would be, or smooth muscle fibers would be stimulated the same. Now, we could have different kinds of stimulus. We could have a mechanical stimulus, which is stretch, like food going through a passageway in your body. We have neural stimulus. Examples of that would be neurotransmitters, like what we learned with cholinergic acetylcholine, or adrenergic norepinephrine, right? It could be different neurotransmitters. We could also have hormonal stimulus, and that travels through the blood. And yeah, like just different types of things. So for this specifically, we're just going to say there is some sort of stimulus, and this stimulus triggers the sarcolemma to open up our calcium channels. And like I said before, they could be voltage gated. I had one like that's voltage gated. They could be voltage gated. They could be mechanically gated. Or they could be chemically gated. There's a lot of different ways that these calcium channels could be opened up. So he's not looking for us to be like that specific unless he gives us a scenario, right? But all we have to know is that, boom, we have received a stimulus and it's telling us, open up your calcium gates. Calcium comes flooding in. We are going from high to low, going from ECF to ICF. The act of a calcium that has a 2 positive charge will depolarize the ICF. The act of depolarizing the ICF creates a change in voltage. And look what we have here. We have very specific voltage gated calcium channels, right? We have to know this. This one specifically is voltage gated. These up here could be anything. Could be chemically gated, mechanically gated, voltage gated, blah, blah, blah. This is specifically voltage gated, so that's very important. These are only open when there is a change in voltage in the ICF from calcium entering. So now, calcium's flooding in. It has triggered this voltage gate to open. And remember, our sarcoplasmic reticulum is a storage zone for calcium. So calcium comes flooding out. And no matter what, we're always going to have super high concentrations of calcium in here. than in here, no matter what's happening, even if calcium's flooding in from the ECF. So calcium comes flooding out, and the first thing that calcium wants to do is to bond with its bestie. It's not thinking about binding to the actin filament. It wants to bind to calmodulin, another protein. So calcium, calmodulin come together and create this molecule. Calcium calmodulin. Easy peasy, right? Now, these two binding actually trigger a change in an enzyme. We have our myosin light chain. Oh, I don't know why I put that again. Myosin light chain kinase. And this myosin light chain kinase at rest is inactive. It's not doing anything. But calcium calmodulin binding together kind of excites it. It's like, yo, let's get the party started. Calcium calmodulin coming together. And there was a girl that was sitting behind me, the one that works with Dr. Kolb. She had this awesome example of calcium is like the girl at the club, right? She's the bad bitch everyone wants to be with. Calcium comes in and she gets the party started. So she's coming in. She has been stimulated to come in. She gets her girl calmodulin, and calcium calmodulin literally get the party started by activating the MLCK from an inactive enzyme to an active enzyme. And that's when I guess the party goes down or whatever. I don't know. I don't club. But now MLCK, this enzyme, is in an active state. And what it does is that it will hydrolyze ATP, give the inorganic phosphate to the myosin head, and also give it the stored potential energy to perform the power stroke. And then ADP is released. Remember, in skeletal muscle, it kind of stays here through the whole process. This one is just more of like, okay, let's hydrolyze this ATP, leave the phosphate and the, stored potential energy in this head so it could do its thing, and ADP gets immediately released. It's important to know, and I mean, this is a little bit extra information. The difference, another huge difference between skeletal and smooth muscle, where calcium molecules will come in and bind to troponin that moves the tropomyosin strand off of these binding sites that we have here, and then it could attach and do its thing, power stroke, blah, blah, blah. It's a little different with this because not only is this stimulating the MLCK inactive to active, this will go over here and together will fit in this key. And it used to, in skeletal muscle, it's called troponin, right? In smooth muscle, that's not the name. It's actually called caldesmon. And caldesmon is only stimulated to do the bend so it can move this tropomyosin strand off of the sites when calcium caldesmon come together, or calcium calmodulin come together and connect to this caldesmon protein, and then this allows everything to happen, right? But that's extra information. You don't have to remember that. I just thought I'd throw that in there. Okay, so what we just did was the contraction. Now how do we go from contraction to smooth, or to relaxation? We have to figure out a way, because now we have all this calcium inside, and that's stimulating this to keep open. That's stimulating this to go from inactive to active. We need this calcium stimulus to stop. Well, the brain will get a signal for these calcium gates in the sarcolemma specifically to stop letting calcium in. Like, these gates will close. So, boom, they're shut. We no longer have calcium flooding in. Well, that doesn't mean anything. We still have a shitload of calcium that's just floating around still, waiting to be bonded, waiting to bond to calmodulin, or it's still bonding to calmodulin and still activating this. It's still moving the tropomyosin strand off of the actin binding site. Well, we need to get all of this shit out. We need, it's 2 a.m. We got to turn on the lights, get everyone going. And no one's going to get going until calcium leaves, because she is the life of the party, right? Well, we have technically 2 different methods, or 2 different proteins, 3 different methods. We have our ATP. This is a primary active transport for calcium specifically. So instead of high to low, because remember, sarcoplasmic reticulum always has a high no matter what, it's going to suck all the calcium, hydrolyze ATP, and bring it back into the sarcoplasmic reticulum to recycle it. So it's sucking all the calcium back in. We also have another calcium ATPase pump working at the sarcolemma. So it's going from ICF all the way to ECF, and it's taking the calcium out. Then we also have a new, like we have our new, that we were introduced with a new primary active transport, we also have another secondary active transport. The first one we learned was the SGLT, and the SGLT worked only because we have our bestie right here working overtime all the time of creating our natural gradient of, we have high potassium, or not gradient, we have our natural, state of high potassium in the cell, low sodium out of the cell. The only way to do that is to keep bringing in more potassium and keep taking out sodium. So she's working all the time. Because she's working all the time, the SGLT pump is able to do its thing. But also, we have this. The only difference between the SGLT pump is sodium and glucose coming in together, which make them, they are co-transporters, right? A symporter. This would be not the case for this one. It's an antiporter, where sodium wants to come in because we created the gradient of high sodium out here, low sodium up here. When this opens up, sodium's like, yeah, I'm coming inside. This is an antiporter, so calcium's actually going to come out too. They're going to go opposite directions. So we have calcium leaving the cell, sodium coming in, and the only reason this happens is because this baby right here is working all the time to set that natural state. So that is how we eliminate calcium in the ICF, by putting it back into the sarcoplasmic reticulum and putting it back into the ECF. So we're not done yet. That triggers, or the act of calcium leaving. Calcium is like, okay, shoot, the party's over, I gotta go home. And her bestie have to separate. You see how they're bonded right here, and now they're separated. So since they're separated, the low levels of calcium will trigger, calcium and calmodulin to separate, because calcium is leaving the cell. We go all the way down here. That will trigger myosin phosphatase right here, which is another enzyme. Myosin phosphatase will come in, and I should probably draw this too. I wanted to do something separate. Oh, actually, I kind of have it right here. So, remember how ATP was hydrolyzed? Like the MLCK to MLCK. ATP gets hydrolyzed. It leaves the inorganic phosphate, goes off as ADP. Well, the myosin phosphatase will come and just take the inorganic phosphate. We'll take it away from the myosin head, and it will actually give it back to ADP floating around to turn it into ATP ready to use. But it's not being used. This is happening all the time, but because calcium and calmodulin are no longer bonded anymore, this does not trigger the MLCK to be active again. It goes the other way. So instead of inactive to active, it's going active to inactive. This is not affected by this. They are two separate enzymes doing their own thing. How Dr. Kolb explained it is that this is kind of just happening all the time, but this going from an inactive to active state will overpower this. This will just be happening so much that this myosin phosphatase cannot take all of the inorganic phosphates because this process is just working in overdrive. But we took calcium out of the situation, right? So now we go from a active myosin light chain kinase into an inactive myosin light chain kinase. This isn't happening anymore. Inorganic phosphates aren't being placed right here anymore. Now, this, oops, I did not want to do that. Now, this process is what's dominating. And if it doesn't have the phosphate in the myosin head, along with the stored potential energy, this cannot perform the power stroke, which means that it's going into a relaxed state. And that is relaxation and contraction of smooth muscle.